Hello, everyone. My name is Ariel Lifshitz, and I will be presenting a paper titled Simple Majority Consensus in Networks with Unreliable Communication. So this paper talks about consensus in message passing systems in which the messages themselves could potentially be lost with some probability. And we present a protocol that attempts to solve consensus with high probability. But first, a quick reminder about consensus. So what is consensus? In the binary consensus problem, we are interested in a system of agents, every one of which is initialized with some binary value, 0, 1. And the goal of a protocol that solves consensus is to have every agent eventually decide on the same value, thus reaching agreement throughout the system. And every protocol that solves consensus exhibits these three properties. The first is decision. Eventually, every agent decides on a value. Agreement. All the agents decide on the same value. And validity. A decision is only made on values that were initially assigned to some agent. And these three properties have to hold for any initial configuration of the agents. That is, no matter in which way all the agents were assigned values, the protocol must solve consensus and exhibit these three properties. So usually, in the pursuit of developing distributed protocols for solving consensus, the literature routinely makes two powerful assumptions. The first is that communication is reliable. That is, all messages that are sent in the system are eventually delivered. And the second is that there exists some upper bound on the delivery times of the messages themselves. And this is the second one is usually made in the context of synchronous systems. However, these assumptions do not naturally coexist. For example, in the internet, where we have the TCP protocol, it guarantees that messages will arrive reliably, but there is no guarantee on an upper bound on when they will be delivered. So is this a problem for us? So the answer is yes, because if the communication is unreliable, then we know that consensus is unsolvable. We know this from the two generals problem. And if there exists no upper bound in delivery times, then we can provide no guarantees on the halting times of the protocols that we design. So instead, let's assume our system is indeed synchronous, but messages arrive by the end of a round with some constant probability Q. That is, if messages do not arrive by the end of the round, we consider them, they may be either lost or maybe they are late. And this happens with some stationary constant probability Q. And since we've introduced this probability into our system, in this context, any protocol that solves consensus only provides probabilistic guarantees. So to summarize, in our model, we have n faultless agents. The agents themselves are fine. The faults are only present in the communication. We assume they are connected by some complete communication graph. That is, every agent can communicate directly with any other agent. We assume they have access to some synchronized global clock, and that time is split into equal communication routes. Also, we assume that message loss events are independent and identically distributed random Bernoulli variables with some parameter Q, and this stays the same throughout the run. In this model, we present the simple majority protocol, which is a protocol that attempts to solve consensus in this context. So it's round-based. That is, in the beginning of every round, an agent sends its value to everyone else, and by the end of the round, it waits for messages from all the other agents, all its neighbors. And it updates its value as follows. So it follows the majority rule, which means that if a majority of the messages the agent receives propose the same value, it adopts this value for the next round. If there's a tie, it readopts its own value. And this protocol continues to run for exactly R rounds, and it terminates after R rounds. And in the end of round R, every agent decides on its current value, and that's its decision value. Okay, so what does this protocol achieve in the model that we have described? So first, if R is equal to 3, and this is our main theorem, then the simple majority protocol solves consensus with high probability. This basically means that in a given run of the simple majority protocol, the probability that consensus will be achieved tends to 1 as n tends to infinity. That is, as the scale of the system grows to infinity, the probability of consensus, of agreement being achieved by the end of the third round tends to 1. Our second theorem says that if R is lower than 3, is smaller than 3, let's say R is 2, then there exists a worst case scenario in which the probability of consensus tends to 0 as n tends to infinity. That is, asymptotically speaking, 3 rounds are not only sufficient, but also a necessary condition for achieving consensus in the simple majority protocol. And our final result states that if there exists a significant initial majority in the set of initial values, that is, in the initial configuration of the agents, if there is a significant majority to one of the values, then the simple majority protocol solves majority consensus with high probability. What does it mean that there is a significant initial majority? And what does it mean, the worst case scenario? To understand these things and to understand the results, we need to go over quickly over a few notations. So the first one is sigma. Sigma is a sequence, an infinite sequence of initial configurations. Okay, so the index in the sequence denotes the number of agents in the system. So for example, C1 is some configuration of a system with 1 agent. C2 is some configuration of a system with 2 agents, and Cn is some configuration of a system with n agents. And this can be any configuration, just some sequence of some infinite sequence of configurations. For example, we have 3 configurations here from an infinite sequence. So C20 is a configuration of a system of 20 agents, and the circles represent agents, and the color is which value they hold. So let's say red is 0 and blue is 1. So in this configuration, initial configuration, there are 7 nodes, 7 agents that start with 0 and 13 agents that start with 1. In C43, we have a lot of agents that start with 0 and a smaller minority that start with 1, and so on. Let's denote by n0 Cn and n1 Cn to be the number of zeros and ones in Cn. So for example, in C20, n0 is equal to 7, n1 is equal to 13. In C43, 29 agents start with 0, so n0 is 29, n1 is 14, so on and so forth. The relative majority of a configuration Cn is defined with, it's denoted by a small delta of Cn, which is defined as the maximum between the number of zeros and the number of ones, minus n divided by n floored. Okay, so in simple terms, this basically means, this is basically the number that represents the excess over 50% of the majority value in the configuration. So for example, in C20, we have 13 ones and 7 zeros, so we have extra 3 ones. So the relative majority of C20 is 3. In C43, we have 8 extra zeros over 50%. That's why the relative majority is 8. And this forms, okay, so the C's are a sequence of configurations, and the deltas form a sequence of their own, a sequence of relative majorities. So delta sigma is the sequence of relative majorities of sigma, which is simply the relative majority of every single one of the configurations in the sequence. So now that we understand the notations, let's go over a lemma. Lemma 1. Let sigma be an infinite sequence of initial configurations. And let sigma prime be the configurations reached after a single round of the simple majority protocol. That is, for example, C prime n is the configuration reached from Cn after one round of the simple majority protocol. Then delta sigma prime is in omega of square root of n with high probability. In simple terms, this basically means as the sequence continues and the system, the size of the system is closer to infinity, then the relative majority of the configuration there after one round of the simple majority protocol is going to be on order of at least square root of n. We have a more formal formal definition of what this means. I will leave this here for the reader. So this is the first lemma. Now this is maybe more intuitive when the relative majority in the beginning was already large. So if it's roughly already I don't know, n plus square root of n, then it's understandable that after one round of a simple majority protocol, it will be larger, the relative majority will be larger than square root of n. But why does this make sense in the worst case scenario, specifically when there exists perfect symmetry? So what I'm saying basically that in this special case, when this configuration is of infinite size and there exists perfect symmetry that the number of ones, number of zeros is equal, after one round of the simple majority protocol, there's going to be a symmetry breakage, and it's going to be, and the relative majority will be on the order of at least square root of n. Why is this the case? So we have some intuition here. So since this is perfectly there is perfect symmetry in this configuration, let's take one of the agents. In the messages that it receives, roughly half of them will be zeros and half of them will be ones. So basically its value after the first round is a coin toss. It's some Bernoulli random variable with a parameter of 1/2. And the probability that the configuration will return to itself after one round is probabilistically 0, because as n tends to infinity, the probability that it will remain exactly symmetrical, it tends to 0. So the symmetry will break somehow. So let's assume the symmetry will break in the way that the ones hold the majority. Then by definition, the relative majority of the configuration Cn will be n1 Cn minus n divided by 2. And this can be expressed as a sum over all the agents of the agent's state minus 1/2, the agent's value minus 1/2. From the central limit theorem, we know that 1 over square root of n times this expression on the right, which is equal to the relative majority, tends to some normally distributed random variable as n tends to infinity. So it converges in distribution to some normal random variable. And since this is independent of n and a bounded number, it's of course in theta of 1, which leads us to the conclusion that the relative majority Cn is in omega of square root of n with high probability. So as n tends to infinity, the relative majority is going to be on order of at least square root of n. Now that we understand the first lemma, let's review a second lemma. Let sigma be an infinite sequence of initial configurations. If delta sigma is already in omega of square root of n, and r is equal to 2, then the probability of majority consensus tends to 1 as n goes to infinity. That is, if the initial majority of the configuration is already large enough, already larger than square root of n, then we will solve consensus in 2 rounds. And not only that, we will solve majority consensus, which means it's basically the same as regular consensus in terms of decision and agreement, but the validity in majority consensus says that the initial majority value is the only valid decision. It means if we have an initial majority of at least square root of n, then that majority will be retained by the simple majority protocol, and consensus will be solved where the decision value was that value. Okay, so if we return to our summary of main results, we can now understand what it says. So if r is equal to 3, the simple majority protocol solves consensus with high probability, and we gain that from the first and the second lemma. The first lemma says that in the worst case scenario, in the perfect symmetry scenario, the relative majority will grow after the first round to be on order of at least square root of n. And from the lemma that we've just seen from lemma 2, we know that if the relative majority is already larger than square root of n, then we only need 2 additional more rounds to achieve consensus. And that's how we gain the r equals 3, which is the sufficiency condition. The second theorem says that 2 rounds are not enough, because in the worst case, in the perfect symmetry case, 2 rounds are not enough to achieve consensus, to achieve agreement more precisely. And the probability of consensus will tend to 0 as n tends to infinity. So r equals 3 is not only sufficient, it is also a necessary condition to achieve consensus with high probability for this protocol. And if there exists a significant initial majority in the set of initial values, so if the relative majority in the configuration is already on order of square root of n, then the simple majority protocol solves majority consensus with high probability, and it does so in at most 2 rounds. Okay, that is basically it. If you have further interest in our work, you are more than welcome to visit the full version of our paper that is stored on the archive. Thank you very much for listening.